Visual trace diagnostics allows for recording and visualizing the software at runtime. That's perhaps something you already understood, but for multitasking embedded software, the source code does not give a full picture of the runtime system. It can seem like a black box, this runtime part, or the dark side of the code, if you will. Visual trace diagnostics gives you a detailed timeline of the runtime behavior and also a large set of visual objects, metrics, and statistics. This makes it far easier to debug system-level issues. By that, I mean problems that are detected when running the full system. And I mean, these can otherwise be quite difficult and time-consuming to resolve. You can also find software design flaws and improve reliability, performance, and reduce the risk of future problems. By software design flaws, I mean suboptimal design solutions that are perhaps not errors, but problematic decisions in the software design. With visual trace diagnostics, you can also measure timing and performance in the software for verification of real-time requirements and for tracking and optimizing the software performance throughout the development. The data collection in Tracealyzer is done in different ways, but typically it relies on a software library. It has very few hardware dependencies, so it works on essentially any processor and doesn't require any extra tracing hardware. This allows for continuous live streaming of trace data from the target system to host, so you can monitor the system over long periods of time. And you can even see live animated views of the data. Software tracing as such is nothing new. I mean, you have vendors like Lauterbach, etc., that have provided different forms of tracing for many, many years. But raw trace data is quite difficult to use in practice. Viewing this in text form isn't really helpful because you get large amounts of low-level information events where most are irrelevant repetitions of the same patterns. You can't see the forest for all the trees. To really benefit from software trace data in everyday development, the solution needs two more components. The data needs to be processed into a meaningful model that describes how each of these events, how the data affects the system state. This requires that the solution understands all the different software services that are traced, like Bartos API calls, not just their name, but what they actually do. The data needs to be visualized to allow quick, intuitive comprehension and actionable insights, even for large data sets. The human brain is very visual and excellent at pattern recognition, especially at spotting anomalies in repeating patterns. And we can leverage this by showing visual overviews from different perspectives, like graphs over CPU load or task response times. Finally, by connecting these overviews with details, we allow for a top-down workflow that is ideal for system-level analysis. You can spot anomalies in high-level overviews and then drill down to inspect the details and learn why the system behaved this way. And we call this visual trace diagnostics. This is really useful for debugging purposes whenever you need a timeline of the software. This is often the case when debugging a full multitasking system, and especially important when the location of the bug isn't obvious from the symptoms, or when the issue is difficult to repeat. Perhaps it only occurs once in a while for no apparent reason, or when interactive source code debugging can't be used, perhaps since the system can't be halted for debugging, or that you physically can't connect a debug probe. While many still use kind of printf debugging in such cases, visual trace diagnostics is actually a superior alternative. This is partly since the logging is much less intrusive. If you compare the tracing we do on a typical 32-bit MCU with printfs over a serial port, this is about 100 times faster and less intrusive. So this allows for logging much more information also in the RTOS kernel, so you get more data. And also the data is easier to analyze, especially for large data sets, thanks to the powerful visualization. This translates into less debugging time and more time available for customer value creation. And with better ability to solve complicated bugs, you reduce the risk of project delays or having to work 100 hours per week to make the deadline. Finally, better insight during debugging means less guesswork involved. This is likely to improve software quality, as you can make sure to fix the bugs properly and not make speculative patches that solves the problem. Here's a basic example of system-level debugging with visual trace diagnostics. This is a very simple example to be easy to explain, but hopefully it gives a better picture. In this case, we're using the serial console UART, normally used for printf debugging, basically. This is a shared resource that is accessed by different parts of this system. And the problem is that on some occasions, the output we see on this UART is sometimes corrupted. You see, we have two different kinds of data here written by different parts of the software. We have about 50 bytes of L characters. Of course, this would be some kind of meaningful data in a real world example, but this is just to make it easier to see. And we have 20 bytes of age data coming in. Once in a while, these interleave, so the data is corrupted. The system starts to write the L data, and then for some reason you get age data. So what's going on here? To analyze this with Tracealyzer, we record a trace of this test case until we see that we have a problem. In the trace view on the right here, you see the RTOS task scheduling and RTOS API calls. These are recorded automatically in supported operating systems. We have also added a user event in the UART driver to capture this data write in the trace. They are shown as yellow labels in the trace. And we can see that there are two different tasks here that are writing to the UART, so they are probably interfering somehow. But the trace is quite long, so how do we find the actual error? We can make use of one of the overviews, the actor instance graph. This is shown on the left, displaying the response times of the tasks, which can reveal interference by higher priority tasks. This view can also show other timing metrics of interest, like execution time, that's the net time used by the task, or periodicity and other metrics. The actor instance graph gives you a high-level overview of the trace. The zoom level here in this example is 10 seconds, so you can see a quite long part of the execution. And by double-clicking on this anomaly we see here in the middle, we open the particular millisecond in the trace where this occurred, well, 15 milliseconds. And we can see that the problem, quite simple example, we have a preemption. The red task here, task high it's called, it preempts a lower priority task that was writing the data. And that's the explanation. So the solution would be to add a mutex to avoid such kind of access conflicts. A mutex allows for mutual exclusion in critical sections. So this is one example of how a symptom detected at system level can be kind of tracked down and analyzed with Tracealyzer to see the explanation. Another important use of visual trace diagnostics is to find software design flaws, and as early as possible. You have probably learned the hard way that designing RTOS-based software is quite challenging. I mean, you have multi-threading, you have limited computation resources, it's limited observability, etc. There are best practices in RTOS software design, and these are important to follow to make sure that your project is successful. By design flaws, we mean deviations from these best practices. They are not necessarily errors, but may reduce performance and responsiveness, increase the risk of future bugs, and make the system testing less effective. And this impact on system testing is especially problematic as it increases the risk of elusive bugs that might leak out into production devices. System testing is affected if, for instance, if design flaws causes the system behavior to become less deterministic, for instance, by introducing unpredictable variations in software timing. The more complexity and the more chaos you have in the system behavior, the more difficult it is to test. You might get race conditions and other problems that might elude detection during the testing. Tracealyzer can help you find such design flaws and ensure that the system is stable and deterministic. And this is really important to find early, because otherwise you might find yourself in debugging hell when the application grows and becomes more complex. And that might necessitate a major redesign of the software in late stages of the project, which could cause project delays. The earlier you can find and fix such design flaws, the fewer changes are typically required. With Tracealyzer, you can find design flaws like excessive dependencies between tasks, unsuitable task priorities, and as mentioned, variations in software timing. These are examples of technical debt, and this has kind of an interest rate that can be really costly to neglect if you keep building and adding complexity on top of a not ideally designed software, a chaotic software, then the result can be a disaster. Here is an interesting example we actually found in official Wi-Fi driver code from one of the major microcontroller vendors. I'm not going to reveal which, then we might get sued or something. We applied Tracealyzer to their IoT demo project that was using Wi-Fi to communicate with the cloud. And we noticed two issues immediately in this trace. But we were stress testing this solution by sending blocks of about 500 bytes repeatedly over the Wi-Fi connection. But we could only get the maximum throughput of about 23 kilobytes. And Wi-Fi is supposed to be a lot faster than that. In the trace view, we can see that it took about 20 milliseconds to send each such block, 500 bytes. And we can also see that the Wi-Fi driver task, that's yellow in this view, is running constantly during this time and consuming all available processor time. This system had a microcontroller, an ARM Cortex-M4 MCU that communicated with a Wi-Fi chip over SPI. And to analyze why the blocks took about 20 milliseconds to send, we inserted a few of these user events in the SPI driver where the data was sent to the Wi-Fi chip. And then we could see that DMA transfers was used for every SPI message. And DMA is efficient for large data transfers since it offloads the processor from the data transmission. But it requires quite a lot of code to set up a DMA transfer, and it was used for every message, even small handshaking messages of just 2 or 4 bytes. And that added up a lot. Each of these transmissions took about 2 milliseconds due to all the DMA setup, which added up to 20 milliseconds per block. This could be solved by adding a condition that checks the message size, and if it's below a certain threshold level, say 100 bytes or so, then perhaps you shouldn't use DMA. Regarding the high CPU load, we noted that the Wi-Fi task didn't suspend while waiting for the SPI transfers to complete. An RTOS task should suspend itself when it's not doing anything useful by calling a suitable RTOS API function, like blocking on a semaphore or queue, or calling a delay function or something like that. Those functions are traced by Tracealyzer, but we can't see any sign of that in the trace. This is a sure sign of busy waiting, where the task is waiting by executing a loop until the condition is met. This is generally considered as bad practice because lower priority tasks are then not able to execute. When digging some more in the code, we found a likely explanation within a few minutes, as can be seen in the lower box here. And the solution is to ensure that the Wi-Fi task uses the appropriate RTOS functions to wait in suspended state instead of using busy waiting loops. This was actually available in the code already, an option, non-blocking TX, as you see in the code example here, but this was not enabled. This is often the case in demo code from MCU vendors because they don't want to tie the demo to any particular RTOS, so they use generic but less efficient solutions like busy waiting instead. That's important to spot when using third-party code like this. Last but not least, visual trace diagnostics can be used to measure software timing and resource usage. You can verify real-time requirements and keep track of software performance and resource usage throughout the development project to avoid that you're surprised by low performance, etc., when you're close to delivery. Tracealyzer provides timing metrics on task instance level. By task instance, we mean a single execution of a task, a job. You can see things like task execution time, response time, and you can also define what we call custom intervals based on user events that you add anywhere in the code and see the time between these user events. That allows for any kind of profiling you would like in your application to see the time from event A to event B, basically. And you can even plot this data as shown on the right, so you can see the variation. And for all these properties, all these data sets, you can see the lowest, highest, and average values. And the extreme value, highest and lowest, they are linked to the corresponding locations in the trace, so you can see their causes. Tracealyzer can also provide resource usage metrics like CPU usage per task, plots over memory usage, and the amount of data sent over an I/O interface, for instance. And that way, you can spot any, you can see how much bandwidth you're using, how much of the CPU each task is using, etc. So by this, you can ensure compliance with real-time requirements of your application, monitor the product performance also, continuously, and also find ways of improving it, because Tracealyzer doesn't just show you the performance, it shows you why you have anomalies in the metrics. And this allows for a more responsive and capable product, improving customer satisfaction and hopefully also sales. And you can, of course, avoid project delays since you can detect any issues with performance or resource usage early and avoid nasty surprises in the end of the project. As of today, Tracealyzer supports embedded Linux and the following list of real-time operating systems. We support these in different ways. For FreeRTOS, for instance, we provide our own trace recorder library that also supports streaming. For ThreadX, we use the existing trace recorder in the ThreadX RTOS. And the same for ARM Kyle RTX 5. They have their own tracer, but don't provide much analysis support for it. MicroCOS 3 is supported in the same way as FreeRTOS with our own tracer, the same with SafeRTOS. For Linux, we are using a third-party open source library called LTTNG. That is an established solution for system tracing on Linux. For VxWorks, we're using Wind River's own tracer included with VxWorks, etc. So the actual data collection is solved in different ways for different platforms, but the visualization and analysis is the same. So to summarize, Tracealyzer is the leading solution for visual trace diagnostics, and you get several important benefits: easier debugging of system level issues, finding software design flaws, and verification of timing and performance. This saves you time and money by less debugging time, reduces the risk of project delays, improves product reliability and performance, and frees up developer time for important customer value creation. It works on essentially any processor, and no extra hardware is required. And that concludes the introduction presentation. Now I have prepared also a demo. And here is Tracealyzer. Currently we're looking at a FreeRTOS trace, but as mentioned, the visualization and analysis capabilities are the same, especially for different RTOSes. For Linux, we have added a few additional features and tweaked it a bit to make it suit the Linux kernel a bit better. I will take a look at your questions right after this. This will be more like a feature walkthrough, maybe 10 minutes, and then I will take a look at the questions, okay? Yes, so let me just get my notes. Yes, so on the left here we see the trace view. Currently this is a bit boring. Let's scroll down a bit here. Here we see different RTOS tasks and interrupts on a vertical timeline. And the reason we have a vertical timeline instead of a traditional horizontal Gantt chart, sorry about the noise, there's a kind of bulldozer in the background. We can show events like this. By events, I mean things like API calls, kernel events, and your own user events that you're adding in the code to get more information. And the meaning of this visualization here, this task trace, is as follows. The solid rectangles here we call fragments. They are uninterrupted execution between two context switches. So basically, the task is executing without disturbances. There might be interrupts that are not traced, then we don't see them, but other than that. If you select a task like that, you see this blue rectangle that indicates an instance. That's the complete execution of a task, basically one iteration in the main loop of a task. And you can see this shaded area in the beginning, that's time where the task has been activated, but it's not yet executing because there are other things executing with higher priority. And if we have a case where there is a preemption, let me find you here, we can difference more clearly. So here we have this orange task running, and the blue rectangle indicating the instance starts all the way up here and goes through here, about 2.7 milliseconds shown here. And this is preempted on at least 2 occasions here by an interrupt that have been traced, and also higher priority task. So there are 3 different fragments within this one instance. In an RTOS, it's important to keep track of your scheduling priorities. We sort the tasks by scheduling priority when showing RTOS traces. And we also assign the colors for the tasks by priority. So red things have high priority, interrupts high priority tasks. And then you have this color scale, as you can see in the CPU load graph here. Each color here corresponds to different tasks. But let's start with the event log. This is the most detailed view in Tracealyzer, basically the data in raw form, so to say. We have formatted it nicely, but this is the kind of data that Trace operates on. And as you can see, there is a lot of information here. This trace is not super long. It's I think it's 3 minutes long, but we have thousands and thousands of events. Working on trace data in this form, even with these color annotations, etc., is quite difficult. Especially, I mean, you can search for things like this in the trace if you're interested in something particular, if you know what you're looking for. Say that you're tracing. We have a user event called target PUS. This application is a PID motor controller. Target PUS is the current set position where the system is aiming for. So let's find those events. And here we go. So here we can see all the events of that kind. You can also, of course, search for many other things like RTOS API calls and things like that. But as you can see, when you double click on an event, you see it in the trace view, and other views are also navigated. But this is kind of a bottom-up analysis, starting from the detailed events and then positioning the trace accordingly. This makes it easier to see the context, what's going on, what other things are executing in this time, what have preceded it, etc. That can be really valuable. But sometimes you're not quite sure what to search for. You might have a high-level symptom in your system. You see an error message, but you're not quite sure what that corresponds to in the code. Then it can be better to use a top-down analysis where you start in the high-level overviews we have and then spot anomalies and drill down to find the locations. And if we take this variable, for instance, this target position, we can see this here in the user event signal plot. This graph shows data from the user events, in this case the PID motor controller, so we can see how the signals are controlled over time. You can see how the target position is updated here, and the current position is updated, and it tries to adjust to this level. And you can also see the motor torque that is applied to reach this. So this gives you a much better overview of the data, and as you can see, it's synchronized with the trace. Each point here in the trace data is actually an event. You can see like this. But I usually show it like this, when otherwise it gets really messy if you try to apply the markers here. So you can see like this. And you can see in the trace what was going on at this time. If you had some kind of weird anomaly in your output of the system, you could see what was happening in the software at this time. Perhaps you had a lot of interrupts or something that disturbed the execution. There are many other ways of overviewing data in Tracealyzer. One example is, let's start with the CPU load graph here. This shows basically a summary for each small section of the trace. It calculates how much time is used by each of the different tasks and interrupts. And you can click on this particular peak here, for instance, and see what was going on here. Why did we have this peak? Or if you're interested here, why is it, what's happening here, like that? And so this gives you not only the levels, but you see the shape of how the variations of the CPU load, and you can find, you can see the reason for this shape, why it appears like this in the trace. So it's a way of navigating the trace data. Another view is the communication flow. This is a high-level overview of the generated from the trace data. Now I have generated from the entire trace, but you can also select a small part of the trace and just generate the communication flow graph for this particular section. Here we didn't get anything. Let's try a slightly larger section. And yeah, so the meaning here is that the rectangles are tasks or interrupts, things that execute. And the ellipses are RTOS objects like queues, mutexes, and things like that, synchronization objects. And this shows you how, basically, who is talking to who and the direction of the data flow or triggering. So the interrupt is sending data to a queue, and the queue is read by this task, etc. You can click on this to see all occurrences of this task, or if you click on this queue, we see all operations on this queue and can find them in the trace like that. This view is called object history. So it's kind of a filtered view for each object. And we can even see the state of the object here. For instance, for a queue, we see the number of messages that are buffered. Let's take a more interesting example. I think that's better. Yeah, here we can see how 2 messages are sent. They're in sequence. Like that, we have 2 messages sent, and then further down they are received. So we can actually track a particular send to the corresponding receive and follow a particular message like that. We'll say that the task is receiving a message and with some bad data, then we can actually we can actually see where the data is generated. I mentioned the measurement of timing properties and things like that. We have the statistics report there. And we get this dialog where we get to select what tasks and what properties to include. And then we get a report like this. Looks pretty boring, but it's important information here. You can see the highest observed execution time, for instance, and especially response time. By execution time, we mean the actual processor time used within the task, while response time is the real time from the start to completion, including all disturbances. And here we can see some interesting differences. For instance, here we can see that this task TC control has a maximum execution time of 188 microseconds, but the response time, the highest response time, is actually 84 milliseconds. If we want to see what happens here, we can just click, and we can see that there is a higher priority task that is running for quite a long time and is preventing this from executing. And this is a kind of a design flaw, that we have a high task that is running for quite a long time. Otherwise, you would typically put if you have a high priority tasks with long execution time, and especially with large variations in execution time, you can see here is a very short, and here it's a very long one. Unpredictable execution like that should generally be on low priority level, so you don't disturb other tasks. Yeah, let me see if I missed something here. Mentioned that one. Yeah, there are a couple of other features. We have another way of measuring, profiling a system. I mentioned that we have these user events, and let's show just this one. This user event called system state, that's a state transition we have logged in the trace. So it's a state machine basically. And we can make Tracealyzer aware of this as a state variable and create a state machine definition. Sorry, wrong button. Let me find the right new state machine. Here we go. So you can create state machines in two ways, either by just selecting the channel that is used for the data, or there's a more advanced method involving regular expressions that is more flexible but more difficult to use. So I just select this user event channel that we're using for user events for this state variable. A user event channel is just a label that we can put on events to basically group them. And now we can see this state over time. This state could be anything, something we're logging in the code. It could be the state of a TCP socket, or the state of a USB connection, or some general application state. And we get a view like this with task execution on the left here, and this particular state variable here. You could put more of these in parallel if you like, and get kind of a logic analyzer view, and you can even compress these like this. If you're interested in, now we see the time here from between these state changes. If you're interested in some arbitrary period between two events, you can create a custom interval. So if we select this, let's try that one. Or let's see now, I think, yeah, stopping. Yeah, let's try the time between. Let me find a good example for you. Stopping until stopped, or so. Yeah, let's try something. Sorry, I need a better example for this. If we select, this is a bit difficult to find at the moment. You need to go to this intervals and state machine, add custom interval, and then you get this dialog. Then you can select an event like that. It needs to be a user event though at the moment. You can give this data set a name. Let's call it test. And then you specify a string to match for the beginning of the interval. Let's take that one. And then something else here, like that one here. And yes, that is correct. Save. Now you see this red thing here. That's a custom interval between these events. This could be, for instance, if you have a USB stack or something, when plugging in a USB connection, a USB socket, the time from the USB processing starts until it's completed, for instance, or the time from the system starts up until it's online. Any kind of application specific profiling. And if you want a report, you can click on this point and see statistics for this interval. See the time between the intervals, the length of the intervals, etc., and find all occurrences like that. For a state machine, you can also get more information. You can see the diagram of the state transitions, so you can actually see what's happening in this with this variable. If there are any weird state transitions that shouldn't be there. If you want statistics, you can go back to this panel where we see our custom data sets, and then you can select, get a statistics report, and here we see the timing of each of these states. So we have 36 occurrences of this state. The system spends 8.3% of the time in this state. The length, the duration of the state is between 40 milliseconds and 1.7 seconds, etc. And if you're interested in a particular min or max value here, you can click it to find it in the trace like that. To get started with Tracealyzer, the easiest way is to just go to our website. Where is that? Okay, I can't open my browser. Oh, it's in the other window, sorry. Tracealyzer.com. Then you go to download and select what operating system you're using, an RTOS or maybe Linux. I will show you the Linux version as well soon. And sign up for an evaluation. By default, you get a 10-day license with full functionality. But if you need more time, you can just contact our support and support@perceptio.com, and we can extend it for you. Let's take a look at the Linux trace. This is something we released just last week, actually. This new Linux version has been in development for over a year, and this took way longer than expected because Linux works in a very different way compared to an RTOS, and we found that we needed somewhat different features. Let me just reset this layout like that. So one thing you will note is that in the Linux system, you of course have a lot more processes and threads, and they can be, the trace can become rather wide like this. It can be difficult to see all the things that are happening. So a Linux trace is much more data and requires a bit more features to allow analysis in a good way. One thing we have, for instance, is this ability to hide inactive things. We call them actors. By actor, we mean an executable object like a thread or a process or a task. So we can hide them like that. That is especially nice when you zoom in a bit, then, because you don't have that many active things. Sorry, I managed to hide them all. Another thing that you will find in the Linux version that is not in our other Tracealyzer versions is this signal and syscall explorer. This is like an index of the trace that shows all references to all processes and also to file descriptors or files that have been included in the trace. So if I know that my application is using a particular file and I'm interested in to see what's happening there, I can just select this. Let's take bin. Yeah, I know that in this trace we are using the ls command to list files in a directory. So I know that we can see here that this ls command is used, and here, and this is the system calls or syscalls that are used by this process. If we zoom in a bit, we see more details, and the purple sections are the syscalls that are executing in the process. So we can see that syscalls are actually responsible for most of the execution time here. And in particular, we have this. That's we click on this, we can see the syscall. That's clone. Yeah, it's spawning a new process or thread. We can see the trace in different ways as well. We have a new perspective. This view, or this option here, shows you different fields that you can add to the trace view, different types of data, different ways of showing it. This is available in the other variants of Tracealyzer 2, but for Linux we now also have this actor tree. And as I mentioned, an actor is an executable. And in the actor tree we can see how the different processes are forked and spawning new. So we can see the relations between them like this. And this is especially obvious if we zoom out a bit. We can see how, oops, let me hide this one. Yeah, here we can see how new processes are forked, created like this. Yeah, apart from that, I mean, all other Tracealyzer features are available. One difference is that in Linux, syscalls are a bit different than RTOS API calls. Syscalls can be quite complex, and while RTOS API calls typically have a rather clean semantics. So for that reason, Tracealyzer for Linux shows syscalls as what we call raw events without any semantics, just basically the
John, there is a few questions on the meeting chat.
Yes.
About Linux. One question from Avi is if there is a support to look into the Linux kernel.
Yes. I mean, you can see what the Linux kernel is doing. You can see scheduling and all the events that are logged, for instance, and things like syscalls. It's not a tool like a Lauterbach for tracing individual functions, because this is using LTTNG, software-based tracing, and that's limits the how deep you can go, so to say. You can't log everything in software, that would cause too much overhead. This is more intended as a tool for application analysis for application developers. There are other tools that can provide more insight at lower levels, I believe. But this can be a nice alternative to like print K calls to print stuff from kernel code with LTTNG events shown in Tracealyzer, and they are much faster. And yeah, let me see if I can, do you have any, let me see, did I answer that question properly, I think?
Yes.
I get confused.
We have also a few questions coming about the footprint that is a requirement on the RAM in order to see on a typical microcontrollers with FreeRTOS, for example, how much RAM buffer we need to allocate in order to see all the recorded events. Okay. When it comes to RAM, if using streaming, then you only need a buffer for a temporary buffer until it's transmitted. And in that case, it can be sufficient with, well, a few kilobytes, like 1 or 2 kilobytes if using a J-Link. They are pretty fast, so they don't need much buffering. If using ITM, you don't need a buffer at all, actually, if you have a fast probe, like a Kyle Ulink Pro or iJet or something like that. If using snapshot mode, where the data is stored in a RAM buffer,
then you can, of course, the length of the trace you get depends on the size of the buffer, but the snapshot recorder we are using for FreeRTOS is quite memory efficient, so it uses between 4 to 8 bytes per event, on average like 6 or 7 bytes. So with a 4 kilobyte RAM buffer, you can typically get something like maybe something like 800 to 1,000 events or so, 500 to 1,000 events. How long that is depends very much on the system, but typically a few hundred milliseconds or so. If you have a large memory, something like a Cortex-A system with megabytes of memory, then you can of course use a much larger RAM buffer if you like, or you could use streaming over a network connection.
Okay.
I have a question regarding to what action should we take in the software. Should we add a special code in the software, or this debugger works automatically in some magic way?
It's not magic, unfortunately. It needs some extra code. Let me show you a picture here. So this is a kind of system illustration here. You have this trace recorder library that contains a buffer, and this needs to be called from the application code and from the RTOS. And depending on what RTOS or operating system you're using, we have different solutions to this. For FreeRTOS, SafeRTOS, and microC OS3, we have our own solution, our own library, with support for both streaming and snapshot. And for Linux and VxWorks and ThreadX, there are existing solutions for this. The way you use this is that you need to call an initialization function. You need to connect it to the RTOS kernel somehow. That's typically by including a header file or something like that. And then you need a way to get the data out. To set this up for, let's take FreeRTOS as example. To integrate the recorder in FreeRTOS, you have this library with a couple of C and H files. You need to take these C files, include in your project, make sure that the header files are included as well. In FreeRTOS, there is a setting called config use trace facility that should be enabled. What that does is that it activates different trace hooks in the kernel. And then you should include our header file and the FreeRTOS configuration file. And what that does is that it populates the trace hooks with our code to log this information. And then you need to call this function in the initialization, like that. And then there are many ways of getting the data out. We have a large section on that. Let's see here. We have, for instance, a plugin for Eclipse IDEs that gives you a Percepio menu within your IDE that makes it easy to take these snapshots. Or if you're using streaming mode, we can interface directly with a Segger J-Link probe or with IAR embedded workbench and read out the data that way. Yeah, here is a picture of this Eclipse plugin. We have tried to make it, to find solutions for as many tool chains as possible, but they all work in different ways, so it's difficult to find this one solution that works for all. We have the back end, so to say, that the data collection needs to be a bit different for different cases. But if you install Tracealyzer from our website, you have this user manual. If you look in section 2, creating and loading traces, the user manual is quite extensive actually, and fairly well written, so it's worth reading. Then you can check under FreeRTOS here, for instance, or whatever OS you're using, Linux, and learn how it's integrated and how you can use it. And then all the different views are then on the high level here shown separately. Any other questions? Is everything crystal clear?
Can I ask for links? So is it using the standard trace that you configure in Linux and takes the information from there and present it with your tools?
I'm sorry, I couldn't quite hear you. It was a bit noisy. Could you repeat the question?
I'm asking for Linux if it's using some trace abilities that Linux has internally, and then log them out to your with your buffers or whatever, JLink, and then expose them to your analyzer.
Yes, that's approximately how it works. For Linux, we're using this LTTNG. This is an open source framework for tracing kernel and user space on Linux. And so I mean that component is free and open source and everything. It's been available for over 10 years. It's very trusted, but this is not a part of the kernel. So you would need to install that separately using Yocto or something. So it needs to be added. In the mainstream Linux distributions, this is often available in Ubuntu, for instance. But for embedded, you typically need to configure this special, add this separately with in your build, for instance, as a Yocto recipe or something. And LTTNG allows you to create trace session, and you can store the data on the local file system, or you could keep it in RAM as a snapshot mode, or you can stream it over network. Tracealyzer can then receive the trace. Let me show you here. Linux target library, yeah, here. So we can connect to a Linux system like this. I don't have one up right now, but you define the IP address or address to the and the certificate or username. Then you can log in and start tracing and collect traces from Linux. Oh, here it is. Oh, sorry. I'm using two screens, and sometimes windows are popping up on the other screen. There it is. Connect like that.
John, there is a question from Ronen, how the performance is affected by when using the library.
It depends on how many events there are traced, but typically, I mean, there are probably three factors that affect this. There are the speed of the processor. The faster processor you have, the less impact from tracing like this, because you're typically not tracing that many events, maybe a few thousand events per second, but you have many millions or even billions of clock cycles per second. So the faster processor, the better, but it scales to 32-bit MCUs running at like 80 megahertz or so. We have even users using it on 16-bit MCUs at 30 megahertz, even though it loads a bit more. The time to store an event is typically on a 32-bit MCU, a few microseconds. If you're storing, say, 5,000 events per second, and it takes like 2 or 3 microseconds, it translates into a CPU load of a few percent or so. So it's some impact. It can be measured, but it's typically not noticeable. But that should be, you should have that in mind. You can't put software events everywhere and don't expect an impact. It will be an impact if you're not careful. But with normal use, it's typically no problem. Related to that, I should mention that this is not official yet, but we are experimenting with using hardware-based tracing from something like a Lauterbach or iSystem or JTrace to generate similar views based on data from the hardware. And that way we avoid an impact from overhead, so to say. But this is not yet available. It's still in development, early development, I should say. So maybe in a year or so.
Can you trace from within an interrupt service routine?
Yes, but you should be careful. If you have an interrupt service routine that is very frequent and short, adding a trace event there could make it significantly longer. Say that you have an ISR that normally takes 5 microseconds, and then you add 2 or 3 microseconds for storing an event. That could have an impact. But normally, if you have ISRs that take a bit longer or that are not very frequent, and by frequent I mean maybe 10 kilohertz or so, normally we can log events, ISRs from Ethernet events and things like that. It's typically no problem. ISRs can be very time critical in some cases, and then you should be careful. But yes, you can.
Yeah, of course, understood. And another question is, are the trace macros universal among different OSs and universal across, thread context versus ISR context? At least in FreeRTOS, you have different APIs for this use case.
Yeah, I think I understand the question. Well, I think the short answer is no. We have made the tracing is currently specific for each RTOS, and the trace macros have assumptions about where they are used, and the RTOS that is used, like name some certain variables in FreeRTOS and things like that. We are working on a general SDK for the trace recorder that will make it easy to integrate this in any RTOS. Maybe you have an in-house platform scheduler thing, or you're using some other RTOS that we're not yet supporting. Then the idea is that you will be able to integrate this using the SDK relatively easy.
So just let me see if I understand it correctly. So if we are working in an environment that we can, we're flipping a flag and we have SDK wrappers to 2 RTOSes, FreeRTOS and ThreadX.
Yeah.
And it's a matter of flipping a flag to switch from one to the other. You don't have to do any source code changes.
Okay.
So if you would like to integrate trace macros, in this case, we will have to if def or something.
Yeah, I mean, we normally, well, if you're using FreeRTOS and ThreadX interchange and can switch it with a flag, the way it would work is that when using FreeRTOS, you would need to use our tracing setup for FreeRTOS and with our own trace recorder. For ThreadX, we're relying on the Express Logic tracer, and then you would need to use that solution. But what you could do once we had the SDK, we actually have beta documentation, so you could start early if you like. But I mean, you could add instrumentation in your wrappers instead, and trace those, and don't trace anything inside the RTOS.
For ThreadX, you will have to have an external piece of device, or you can over UART or Ethernet. Trace it over communication.
For ThreadX at the moment, we're relying on the Express Logic tracer, and that only supports tracing to a RAM buffer. And then you need to read it out with a debug probe or something afterwards. We are just starting on a project to basically merge our recorder with the existing ThreadX tracing. So we will basically pull out the data using the back end of our recorder, so we can see it in Tracealyzer and stream it. But we're just starting with that, so I can't really say much more at the moment, but it's coming.
I understand. Okay, thanks.
Any other questions? Okay. Then thanks for having me. Thanks for your time. Thanks for joining. Really appreciated. I hope that you find this useful. Try and get started with an evaluation. If you have any problems, contact support@percepio.com or ask Ohad, and we'll try to help you along. Thank you.
We encourage you to go to the Percepio website and download 30 days evaluation. Thanks, everybody.
Thank you.
Have a good day.
Thank you very much.